You know how sometimes a tiny mosquito landing on your arm feels like almost nothing?
Barely notice it.
But then a single fast-moving drop of water, like in heavy rain, can actually sting.
Yeah, definitely feels different.
Both are small things hitting you, but that oop feels totally different. What's going on there?
Well, that difference, it points directly to the concepts we're digging into today.
Ah,
It's not just about how big something is or, how fast it's moving by itself.
okay.
It's about the combination of those things and, crucially, how that combination changes when things interact.
Exactly. Welcome, everyone, to this deep dive.
Glad to be here.
We've got a whole bunch of material here, notes, articles, data sheets, all focused on a really core topic in grade 12 physical sciences.
Momentum and impulse.
That's it. And our goal today is pretty straightforward. Cut through the complexity, pull out the essential stuff you need to really get these concepts.
Yeah, think of this as like your shortcut to understanding the key takeaways. We'll clarify things, get you ready.
We'll unpack what momentum actually is, how forces affect it over time.
The really powerful idea of conservation, especially in collisions.
Right, and how we classify those collisions, elastic, inelastic.
And look at some really important real-world applications, too. Safety stuff, mostly.
Okay, so let's start simple. At its heart, what is momentum?
Well, it's described as a property, right? Something every moving object possesses.
Like a measure of how much mass is in motion. Is that a fair way to put it?
Yeah, that's a pretty good conceptual handle.
Yeah.
And the formula itself, you see it right there in the materials, it's actually quite simple.
P, M, V.
Exactly. Momentum, which we use P for, is just the product of the object's mass, M, and its velocity, V.
And units are crucial here. The notes stress this early on. Mass has to be in kilograms, kg.
Yep, standard SI units.
And velocity must be in meters per second, ma'am.
Right. So if you get grams or kilometers per hour,
Convert first. Always step one.
always. And here's another critical point, something you absolutely can't forget.
What's that?
Momentum is a vector.
Meaning it has magnitude and direction.
Precisely. It's not just how much momentum, calculated by MV, but also which way.
So when you're doing problems, you have to, what, pick a positive direction?
You have to. Choose a direction, maybe right or up, call that positive, then stick with it.
So anything moving the opposite way gets a negative velocity.
And therefore negative momentum. Yeah. Using those plus and minus signs correctly is key for calculations.
Okay, so that vector thing helps with my mosquito versus water droplet question, right?
It does. The mosquito, it has such a tiny mass. M is incredibly small.
Right.
So even if it flies reasonably fast, its momentum, POMV, is just on 2. Well, it's tiny.
Okay.
The water droplet, maybe slightly bigger mass, maybe moving faster, could have more momentum to start with.
But you said that's only part of the story for the impact feeling.
Right, because momentum is just the state before the impact.
Yeah.
We need to talk about how that momentum changes.
Okay, so we know what momentum is. Direction matters. How do we actually change it? How does an object's momentum get altered?
Well, this brings us right to Newton's second law. But maybe not the version you immediately think of.
Oh, that's not.
That's one version, absolutely valid. But the materials here emphasize another form, which is just as fundamental, maybe even more so in some ways.
Which is?
Fan net, F net.
Okay, F net.
Yeah.
That's the net force, the overall force, equals delta. P delta means change in. So change in momentum.
Right.
Divided by delta T, the change in time, or the time interval.
Exactly. So the net force acting on an object is equal to the rate at which its momentum changes.
Rate of change. So how quickly the momentum changes.
Precisely. A net force causes momentum to change over time. If you apply a bigger net force,
You get a bigger change in momentum in the same amount of time.
or if you apply the same force for a longer time,
You also get a bigger change in momentum.
you got it. It
Nice.
directly connects the force to its effect on the object's state of motion, its momentum.
Okay, got it. Force delivers a change in momentum, and that change in momentum is just the final momentum minus the initial momentum.
Exactly right. Take
Yeah.
it off final potential.
Or using the formula, echo upel is mvf mb.
Perfect. Where VCO is final velocity, V is initial velocity. And remember, velocity is a vector, so this change is also a vector. It has direction.
Okay, and isn't there a specific name for the thing that causes this change, related to the force and the time?
Yes. You're thinking of impulse.
The impulse, right.
Impulse, usually written as I, is defined simply as the product of the net force and the time interval it acts over.
So impulse effet head.
That's the definition.
And wait, effet Then if you multiply both sides by it,
you get Fnet ek echo.
which means impulse equals the change in momentum.
Bingo. That's the impulse momentum theorem. It's a really central idea here.
Fet ep. That looks powerful.
It is incredibly useful. It explicitly links the action of the force over time, the impulse, to the resulting change in the object's motion, change in momentum.
And the units work out too. Impulse is Newton seconds, ns.
And change in momentum is kilogram meters per second, kilogram is?
The theorem shows they're equivalent measures of the same thing.
Exactly. And just like momentum and its change, impulse is also a vector. Its direction is the same as the net force's direction.
Ah, okay. So let's loop back to my mosquito and the water droplet again.
What?
The difference in how they feel isn't just about their starting momentum. It's about what happens when they hit my skin and stop, right?
Right. They both undergo a change in momentum. They go from some initial momentum down to zero.
So they both have an ep.
They do. But the time, the et, it takes for that change to happen is probably very different.
How so?
The mosquito, maybe it lands relatively gently. Its body might deform slightly. It slows down over a fraction of a second, maybe a slightly longer et.
Okay.
A fast-moving water droplet hits your skin and splat. It stops almost instantly. A much, much smaller et.
And since Fnet, if ep is, let's say, roughly similar, or maybe even bigger for the faster droplet,
But et is way smaller for the droplet.
then the force, Fnet, must be much, much larger for the droplet. That's the sting.
You've nailed it. The sting comes from that larger average force being delivered because the time interval of the impact, the time to change the momentum to zero, is so short.
Wow. Okay.
And this exact principle, managing the force by manipulating the time of impact for a given momentum change, that's the absolute cornerstone of safety design.
Right. This is where the physics becomes incredibly practical, life-saving even. The notes are full of examples based on this impulse momentum theorem.
Absolutely. Think about a car crash scenario. A person inside is moving, they have momentum.
And they need to stop. Their momentum needs to go to zero.
Right. That means there has to be a change in momentum.
Yeah.
And therefore, there has to be an impulse acting on them to cause that change.
You can't avoid the impulse if you want to stop.
Nope. But what safety features can do is play with the components of that impulse. They aim to dramatically increase the time over which that momentum change occurs.
And if 8 goes up, for the same app,
The average force, Fnet, must go down.
spreading the impact out over time reduces the force experienced at any given moment.
Exactly. Less force means less injury.
So what are some classic examples from the notes?
Well, the big ones are things like airbags in cars.
Okay, how do they work on this principle?
They inflate rapidly, providing a cushion. Instead of your head hitting the hard dashboard very quickly, small at, large Fnet, you hit the airbag, which compresses.
Ah, so the compression increases the time it takes for your head to slow down.
Precisely. Longer at, smaller average Fnet on your head and neck.
Makes sense? What else?
Crumple zones. The front and back ends of cars are designed to crush and deform in a collision.
That always looked like a design flaw, but it's intentional.
Absolutely intentional. The crushing takes time. It increases the duration of the collision itself, the it over which the car and its occupants come to a halt.
Shielding the passenger compartment by sacrificing the ends.
Exactly. Again, longer weight means lower average force transmitted to the people inside.
Seatbelts too?
Yep. They're designed to stretch slightly under load. That little bit of stretch increases the time it takes for your body to stop at the car.
And they spread the force across stronger parts of the body.
Right. Longer time and better force distribution. Also, think about arrestor beds.
Those gravel pits for runaway trucks.
Yeah. A truck rolling into deep gravel sinks in and slows down over a considerable distance, meaning a long time interval.
Compared to hitting a concrete wall, which would be a very short up.
And a catastrophic force.
Huh?
The gravel bed applies a much smaller stopping force over a much longer time to achieve the same change in momentum from moving to stopped.
And padding. Like in sports.
Same idea. Gymnastics mats, helmet liners, catcher's mitts, they all compress on impact.
Increasing the time it takes for the body part or the ball to come to rest.
Reducing the average impact force, Fnet. It's all Fnet by action.
It's amazing how universal that is. The notes even mention using it the other way around, like in sports for follow-through.
Exactly. When you hit a golf ball or a baseball, you want to maximize the change in the ball's momentum, right? Get it moving as fast as possible.
So you want a big up.
Which means you need a big impulse, Ned. You try to apply your maximum force, Fnet, for the longest possible time.
That's the follow-through, keeping the bat or club in contact with the ball for as long as you can.
Yep. Maximize date to maximize the impulse delivered, maximizing the change in momentum, and therefore the final speed of the ball. Same physics, different goal.
Okay, that covers how forces and impulse change momentum for a single object. What about systems? When objects interact, like billiard balls colliding.
Right. Now we shift focus a bit. This is where the principle of conservation of linear momentum becomes really important.
Conservation, meaning something stays the same.
Exactly. But it applies under specific conditions. It applies to what we call an isolated system.
Isolated system, what does that mean, practically speaking?
The notes define it clearly. It's a system where the net external force acting on all the objects within the system is zero, or at least negligible.
External force, as opposed to?
Internal forces. Think about two billiard balls colliding. The force ball A exerts on ball B, and the equal and opposite force ball B exerts on ball A during the collision. Those are internal forces. They act between objects within the system we're looking at, the two balls.
Okay, so external forces are from outside that system.
Right. Things like friction with the table surface or air resistance, or if someone gives one of the balls an extra push from the outside during the collision.
So if we can ignore those outside forces, maybe because the collision is really quick and the impact forces are huge compared to friction?
Then we can approximate the system as isolated.
And if the system is isolated, what does the conservation principle tell us?
It's a fundamental law. In an isolated system, the total linear momentum of the system remains constant. It's conserved.
Total momentum, you mean add up the momentum of everything in the system?
Yes. The sum of the momenta of all objects in the system before an interaction, like a collision, is equal to the sum of the momenta of all objects after the interaction.
So the equation is epinitial up final. The Greek letter sigma for sum of.
That's the one. If you have two objects, say A and B, colliding in an isolated system then, MAVAI plus MBVBI plus MEVAF, plus MEVBF.
Momentum of A before plus momentum of B before equals momentum of A after plus momentum of B after.
Exactly. Remembering that all those velocities V are vectors, so you need your positive and negative signs for direction in the calculation.
The billiard ball example in the study material seems to walk through setting that up. Calculate initial momenta, sum them, set that equal to the sum of final momenta.
And often you use that equation to solve for an unknown final velocity, perhaps.
Why is momentum conserved, though? Is there a deeper reason?
There is, and it connects back beautifully to Newton's third law.
Action-reaction.
Exactly. During the collision, the force A exerts on B, let's call it FAB, is equal in magnitude and opposite in direction to the force B exerts on A, FBA. So FAB, FBA. These forces act for the same brief time interval. So the impulse A exerts on B, FABB, is equal and opposite to the impulse B exerts on A, FBA.
Equal and opposite impulses.
And since impulse equals change in momentum, the change in momentum of B due to the collision is equal in magnitude and opposite in direction to the change in momentum of A. So FBB equals 0.
So if you add their changes together, FBA plus FB equals 0.
Right. The total change in momentum for the system as a whole is 0. If the total change is 0, it means the total momentum didn't change. It remained constant. It was conserved.
Wow, that's elegant how those laws interconnect. Okay, so momentum is conserved in isolated systems, but I remember seeing something about different types of collisions in the notes, elastic and inelastic.
Yes. While momentum is conserved in any collision within an isolated system, we can further classify collisions based on what happens to the kinetic energy.
Kinetic energy, energy of motion, right?
No.
EKA equals 12 mV2.
That's the one. So first type, elastic collisions.
What defines an elastic collision?
An elastic collision happening in an isolated system is one where both total momentum and total kinetic energy are conserved.
Both conserved. So the total KE before equals the total KE after.
Exactly. No kinetic energy is lost or converted into other forms like heat or sound during the collision. Think of idealized, perfectly bouncy collisions.
Okay. And the other type? Inelastic.
In an inelastic collision, also in an isolated system, total momentum is still conserved. That's always true for isolated systems.
Right.
But total kinetic energy is not conserved.
So some kinetic energy is lost.
Typically, yes.
Yeah.
It gets transformed into other energy forms. Maybe heat is generated, maybe there's a sound produced, maybe the objects get permanently bent or dented, that deflation takes energy.
So momentum conservation tells us if the system is isolated. How do I actually tell if a specific collision is elastic or inelastic then?
You have to do the calculation. First, you confirm momentum is conserved. or assume it is if the system is stated as isolated. Then you calculate the total kinetic energy of all objects in the system before the collision.
Sum up all the 12 MeV2 initial values.
Right. Then you calculate the total kinetic energy of all objects after the collision.
Sum up all the 12 MeV2 final values.
And then you compare them. If technicial equals mech final, the collision was elastic.
And if technicial is not equal to tech final,
then it's inelastic. Usually for macroscopic collisions, you'll find tech final is less than mechanicial, meaning some kinetic energy was lost.
The notes had that billiard ball example again, I think, where they calculated the KE before and after.
Yes, and if you run the numbers, the total KE after the collision in that specific example is actually less than the total KE before.
Proving it was inelastic, even though it looked pretty bouncy.
Exactly. Most real-world collisions you see, cars bumping, balls hitting walls, even seemingly bouncy ones, are actually inelastic to some degree. Some energy is always lost to sound, heat, or slight deformation. Perfectly elastic collisions are more of an idealization, though some atomic and subatomic collisions come very close.
Okay, that distinction makes sense. We've really covered a lot here. Momentum itself, impulse changing it, conservation in isolated systems, and the energy aspect in collisions. Before we wrap up, let's distill this. What are the absolute must-do practical steps for tackling problems involving momentum and impulse based on everything we've seen in the materials?
Good idea. The notes really emphasize a few key things for successfully solving these problems.
Number 1.
Diagrams and direction. Always, always draw a simple sketch of the situation, and crucially, choose a positive direction, like right or up, and clearly label it. This is vital for getting your vector signs right.
Okay. Draw, choose direction. What's next?
SI units. Check every value you're given. Mass must be in kg, velocity must be in ems. Convert anything else before you plug it into any formulas. Don't wait until the end.
Got it. Units first, then.
Use the right formulas. Know which equation applies. PMMV for momentum, Finette-Apport for Newton's second law, impulse finite, the theorem finite, conservation tep initial sip final, and EKEK and 12 MeV2 for kinetic energy checks.
Makes sense. Pick the right tool for the job.
And pay meticulous attention to the signs. Positive and negative signs indicate direction for all vector quantities. Velocity, momentum, impulse, force. A drop sign completely changes the answer.
Crucial for vectors. Anything else?
Vector answers need direction. If a question asks for velocity or impulse or momentum change, and these are vectors, your final answer isn't complete without magnitude, units, and direction. Example, 10 kilograms to the left or 10 kilograms west, unless it specifically asks for just the magnitude.
Good point. Be precise.
And one last thing. When calculating impulse, remember Finette or EP applies to a specific object or system. If you need the impulse on object A, use the net force on A and the time, or calculate the change in momentum of A. Don't mix data from different objects inappropriately.
Focus on the object in question. Okay, that's a solid checklist. Following those steps seems like the path to getting his calculations right.
It really does remove a lot of the potential confusion. It's about applying these core ideas systematically.
So just to recap for everyone listening, we've journeyed through momentum, basically mass in motion, PMV. We saw how forces applied over time create impulse, Finette, which directly equals the change in momentum.
Then we explored how, in isolated systems where external forces are negligible, the total momentum before an interaction equals the total momentum after the principle of conservation of linear momentum.
Rooted in Newton's third law, no less. And finally, we learned to classify collisions based on whether kinetic energy is also conserved, elastic or not inelastic.
Understanding these interconnected principles really gives you the power to analyze motion and interactions in a huge variety of situations.
From the sting of a raindrop.
The car safety systems, rocket propulsion, even understanding collisions at the atomic level, it's fundamental stuff.
It really highlights how a few core physics ideas explain so much about how the world works.
And, thinking even bigger, this principle, the conservation of linear momentum, it's not just for billiard balls or cars. It's considered a fundamental symmetry of nature. It holds true for the entire universe, as far as we understand.
The whole universe. Wow. So here's a final thought to leave you with.
If total momentum is conserved across the cosmos, how does this deep principle visible in everyday collisions? The recoil of a rifle, the intricate dance of galaxies over billions of years. How does it point towards a fundamental interconnectedness, a sort of underlying balance in the physical laws that govern absolutely everything?
Something to ponder. It suggests the universe operates as this vast interactive system where momentum is constantly being exchanged but never truly lost.